Let's talk about the labs. Let's talk about gamma ray spectroscopy. This may sound a little familiar because I think all of you have already heard this once. Actually, if you've already gone through this sequence of labs and I come across anything that you're still not clear on, just stop me. Let me know. Okay, so gamma ray spectroscopy. So what do you all think of when you hear gamma rays? Yeah, so very high energy, they're a nuclear reaction. So these gamma rays originate from interactions in the atomic nucleus. In our case, we're going to use cesium-137 as our source of gamma rays. Okay? And this is an unstable isotope of cesium, and it decays via beta decay. So in beta decay, you're emitting an electron from the nucleus. Okay? At its most fundamental, beta decay is a neutron decaying into a proton, an electron, and an electron antineutrino. Okay? In cesium's case, what we're going to have is cesium's going to decay into barium, plus an electron. So the neutron decays into a proton, so this number increments by 1, plus an electron antineutrino. And the total energy released in that interaction, or that decay, is 1176 kiloelectron volts. Okay, so what does this decay look like? This doesn't give us our gamma ray, right? This is just a particle decaying into a bunch of other particles. There's no gamma ray. The way we get to our gamma ray is by looking at the barium, which is what you all do in the second lab in this sequence. You actually look at the half-life of barium and measure that very carefully.
Would the antineutrino annihilate the gamma ray?
Geez, I don't know. I don't think so. I mean, the neutrinos don't interact, right? They have a very, very tiny cross-section. So they would travel. It would be a pretty low probability. It wouldn't be a terribly reliable source of gamma rays. You might get a gamma ray per millennia out of it. But yeah, so our source of gammas is from the barium decaying to the ground state. So yeah, the way this looks is you have your cesium, and it decays via 2 channels. So in one channel, you end up with an excited state barium nucleus. And this happens about 95% of the time. It's far and away the most common. And to work out that probabilities, you have to go through the full quantum mechanical treatment of this decay. Okay. The other 5% decay to the ground state. Okay, so our excited state barium nucleus, when it relaxes to the ground state, it emits your gamma ray. Okay. So any questions about that? That's how we get our gammas. Okay? So now let's talk about what we're going to do with them. So our job throughout the course of this first lab is to build and calibrate a very reliable detector for these gamma rays. Gamma rays are notoriously difficult to detect, right? They pretty much destroy whatever they hit. They're very high energy, very hard to detect. There are only a few good ways of looking at them. The way we're going to use is a scintillation counter. Okay, and in our case, it's a sodium iodide crystal attached to a photomultiplier tube. So we have our crystal, and on the back of this is a photomultiplier tube. And that goes out to your detection electronics. Okay? So the idea with this detector is that we're going to take a bunch of incoming gamma rays and we're going to convert them to something usable, something that we can say is proportional to the energy of the gamma rays. Okay? The way we're going to do this is these gamma rays are going to come in and interact with the sodium iodide crystal. So two things are going to happen in that crystal. There are two physical effects that you need to be aware of. The first is the photoelectric effect. Okay. Which you'll be very familiar with by the time you get here. So the energy of your electron. So okay, let me back up a minute. So in the photoelectric effect, you have complete absorption of the photon by an electron. Okay. So the electron absorbs the energy of the gamma ray. The energy, the resultant kinetic energy of that electron is given by the energy of the incoming photon that it absorbed minus the work function, which is some property of the material. Okay, so you have an electron with some kinetic energy. Okay. What's going to happen is that that electron with a given energy is going to interact with the rest of the crystal lattice. Okay, so it's going to take the energy of that gamma ray and spread it out to the entire crystal lattice. Okay?
Does that only happen with metals?
It can happen with crystals too. It can happen in any sort of arrangement where there's where there's kind of a conduction band of electrons, and that's very common in crystal lattices.
Okay.
Okay.
Is it just that the work function is lower in metals usually? Because the electron's not bound.
Right. So typically in the photoelectric effect lab, right, you dealt with a metal, and in that case you can use visible light photons, much lower energy. So the work function is much smaller. Okay. In the sodium iodide crystal, the work function is much larger. Okay, because actually what your work function is determined by is the electron orbital configuration, right? So you're actually stripping electrons off of that sodium iodide structure. Okay. So you take the electron with this given energy, and that electron interacts with the rest of the lattice. So it deposits its energy either through direct absorption, through scattering, into the other electrons in the crystal lattice. Then what happens that's really useful? So we've taken our gamma ray and we've kind of split it up into a bunch of usable chunks. Okay? What happens then is that you have this big photon whose energy is distributed across a lot of different parts. Okay? So when those electrons de-excite back to the ground state configuration, they don't emit gamma rays, they don't emit X-rays, they emit visible and UV light photons, which we know how to detect. Okay, we can build good, reliable detectors for visible light photons. Okay, so that's what this photomultiplier tube does. So it takes the resultant flash of visible and UV light photons that come out of this crystal and converts it into an electrical signal that we can use. Okay? So that's the process there. The other process at play is the Compton effect. Now, the key difference between the photoelectric effect and the Compton effect is that you don't have complete absorption of the gamma ray photon. After a Compton interaction, the gamma ray photon is still there. It has less energy. It can have significantly less energy, but it's not a complete absorption. And so that gamma ray photon will go on to interact with it can interact with other electrons in the crystal, or it can leave the crystal entirely without interacting again. Okay? So what that is the Compton effect is a scattering relationship. So you have your incoming gamma ray, and you have your electron, okay? And the two scatter off of one another. So you have your photon and your electron both moving off of the area of interaction, okay? Now, what happens with this electron is the same thing that happens in the photoelectric effect, okay? You get you get the energy of that electron continually deposited in the rest of the lattice, converted into visible and UV light photons, okay? But the important point here is that some minimum amount of energy is still going to go into this gamma ray, all right? And if you look in the lab write-ups, you'll see the energy equation for this. And you'll see that there has to be a gap between the photoelectric effect and the Compton effect, all right? Because there's always some energy that's being carried off by the gamma ray, okay? And this will manifest itself in the data you see. Okay.
Can't the gamma ray just carry off a very, very small amount of energy, or an amount of energy that is similar to the work function? And then it wouldn't look like there's a gamma?
It's never that small. Okay? There's always, in the case of this gamma ray, it's always at least 100 EV, 100 keV.
Okay.
I can't remember exactly where the Compton edge is, but we're going to talk about that in just a minute. Okay, so what are you going to see on the output? All right? What you're going to see is pulses. On your oscilloscope, you're going to see a series of pulses. And, well, let's see, how do I want to draw this? Okay, yeah. So you're going to see a pulse that looks something like that. The rapid rising edge and a slowly tailing off edge from the energy being depleted out of the photomultiplier tube, okay? And this is not going to be this clean on your scope trace, okay? This is going to have a lot of noise on it, all right? But, so this is the photo peak. This is the peak due to the photoelectric effect, all right? You're also going to see a bunch of smaller pulses underneath this, okay? And these are going to be pulses due to the Compton effect. The important thing to notice here is that with the Compton effect, you can have a range of energies, all right? With the photo peak, you're going to have one pretty good reliable indicator, okay? With the Compton, you're going to have a big range of energies that can be translated into pulses on your scope trace, okay? So your task over the course of the next 2 weeks is to take this information, because this is all you have, is to take this information and turn this into a good spectroscopy technique for gamma rays, all right? So there's a lot of stuff to be done here. We're going to look at the full spectrum, okay? We're going to calibrate this using the cesium source and then apply our spectroscopic techniques to an unknown gamma ray source. Well, it's not unknown, it's cobalt. But for our purposes, we don't know what the cobalt spectrum looks like, right? If any of you do, you're pretty much done. But yeah, so the point is to take the cesium spectrum, use it to calibrate this detector, and then take an unknown gamma ray source and perform spectroscopy on that source, okay? And then you're going to take this whole setup and you're going to use this basically until the end of the semester, all right? You're going to do a whole bunch of stuff with these tools, all right? You're going to look at radioactive decay of barium. You're going to look at attenuation, okay? You're going to do a whole bunch of statistics, okay? Any questions? Okay, so that's the first lab. That's gamma ray spectroscopy. Okay, so the next lab is X-ray diffraction. And we're going to start similarly to how we started the gamma ray lab. We're going to start with our X-ray source, okay? So in X-ray diffraction, what we're going to do is we're going to start off with a filament, okay? And we're going to run current through this filament. And when we run current through a filament, it's going to emit electrons from the surface, just like a normal light bulb. Okay? So you're going to have electrons coming off the surface, and we're running a current I through that filament, okay? Then what we're going to do is we're going to set up a target. And this target's made out of molybdenum, okay? And what we're going to do is we're going to apply an accelerating potential to these electrons. Okay? So between here and here, we're going to apply a potential. And this potential is big. 30, 35 kiloelectron volt, or kilovolts, okay? So with a number like that, you really expect the electrons to be moving when they hit that target, all right? They're going to be moving at, in fact, X-ray energies, all right? And what we're going to get out, so these electrons are going to slam into this surface. And there are a couple different physical processes here that are going to generate our X-rays. The first one is called Bremsstrahlung. Did I get that right? Yeah. And Bremsstrahlung is braking radiation, okay? So you have an ion in this molybdenum, okay? And you have an electron that's going to travel near but not collide with this ion, all right? And what's going to happen as this electron approaches the ion? Right. It's going to turn. Okay?
So just the nucleus, the ion.
Yeah, it's a crystal, so we can treat it as just an ion. The electrons are out there. So when it turns, to conserve momentum, right, to conserve angular momentum, if we just look at this electron moving along a straight line, it has no angular momentum. When it starts to turn, angular momentum is introduced to the system. So in order for angular momentum to be conserved, this has to emit a photon. Okay? And in fact, this is going to be an X-ray photon. Okay? Now, an important point here is that there's nothing special about this particular configuration, right? This electron and this ion can be coming in at a range of distances with respect to one another, all right? There's nothing discrete about this process at all. So what you end up with is a fairly broad spectrum. Okay, so now if I look at the intensity of light coming out as a function of the wavelength, then I get something like this. Okay? And this is over a fairly broad range of wavelengths. Okay? Now the other physics at play here is just line radiation. Okay? So you have your electron. The energy of that electron is completely absorbed. Okay? It excites up an atom to an excited state. Okay? And when it relaxes, light's emitted. Okay? So that happens between in this wow. That's not safe. So in our configuration, we're looking at K-shell electrons in the molybdenum, and they're being excited up. This is just the most common transition. We're looking at excitations up to the L shell and up to the M shell. Okay? Now these are discrete events. Okay? So you expect to see sharp transition lines coming out the other side. All right? Now, on top of this spectrum, what this ends up looking like are sharp peaks on top of the bremsstrahlung. Okay? And this is the K beta peak, and this is the K alpha peak. So K alpha is the transition between here and here. K beta is the transition between here and here. Okay, so this is higher energy, shorter wavelength. Okay? So this is where we get our X-ray spectrum from. Any questions about that? You'll get it back. Any questions? Okay, so let's talk about what we're going to do with them. Just like in the gamma ray lab, we're actually going to build a very sensitive X-ray spectrometer. Okay? And the way we're going to build our spectrometer is utilizing the principles of diffraction. Okay, so who can remind me how single-slit diffraction works? Should be able to, because you've already seen this lecture once, right? So if I have a single slit and some incident plane wave, what's important about what comes out the other side? Right, right. So you're going to end up with rays coming out here, rays coming out here. And so this remember that this only works if your screen that you're looking at is well far away from this slit compared to the size of the slit. Okay? So the important point here is this path length difference. So you have some angle, right? And so your interference condition is given by d sine theta, where this, this is your distance d, is equal to n lambda, okay? Right? Okay, so how does this apply to our crystal? In a crystal, we have a regular arrangement of atoms, okay? And let's say we have our gamma ray coming in at some angle theta, okay? Now this gamma ray is going to interact with this top level of the crystal and reflect off, okay? Now let's say we have another gamma ray that comes in, and instead of interacting with the top layer, it interacts with the next layer down. Okay? So I can draw straight lines through all of this, right? Now, how is this situation similar? Okay? We still have a path length difference, right? So the gamma rays that come through this path are going to go on, geez, I really made a mess of that picture, didn't I? Okay. So the geometry is the same, right? If I just look at this half, right? The gamma ray, or the X-ray, sorry, has traveled a distance d sine theta. This is your angle theta, right? This X-ray has traveled a distance d sine theta longer than the X-ray on the top. If I look at the other side, it's traveled another d sine theta. All right? So that's the difference between looking at the crystal and looking at the single slit. There's a factor of 2. 2d sine theta is equal to n lambda. And this is called Bragg diffraction. Okay? So this is what's happening within the crystal. Now, okay, so this is the physics that we're going to use to build our spectrometer. So the actual device we're going to look at is very similar to this picture. Okay? It's just turned a little bit. So we're going to have our X-ray source over here, which is this kind of box, right, with your filament. Okay, and the X-rays are going to come out through here, okay? And we're going to collimate them so there's just one nice beam of X-rays. Then we're going to have it hit a tilted target, okay? So the X-rays are going to hit this target and reflect off. Okay? Now these angles are very shallow, all right? If we tilt this too much, the X-rays will just be completely absorbed. Okay, so this angle is going to be less than about 10 degrees. So this is what we call a grazing incidence configuration. And what we're going to have is, let me draw this a little shallower so I can fit the detector in. Then we're going to position our detector up here. Okay, and this is just a Geiger-Muller tube. So it's like a Geiger counter. Now, this configuration is identical to this. So we're going to have this be an angle theta, right there. And this will be an angle 2 theta. Okay? Now if I turn this by theta, it's exactly this picture. Right? Make sense? You have theta on this side, theta on that side. If I turn it, then you have 0 on this side and 2 theta on the other side. Right? So this is our spectrometer. Now, what do we get out the other side? So what are we scanning here? We're scanning theta, right? We're putting in a continuous spectrum of X-rays, and we're just turning it by theta and seeing what happens at a detector. Okay? So if I scan theta, boxing the wrong one. If I scan theta, I'm also scanning wavelength, right? So given our interference condition, what are we going to get out the other side?
You're going to get more counts for the wavelengths that correspond to the transitions?
That's right. We're basically going to completely replicate this, right? So scanning theta is the same as scanning lambda, right? Keep in mind that theta is small, right? So it's not repeating. So scanning theta gives us exactly this spectrum. All we're doing is just changing the angle. And what this crystal is going to give us out of the other end, because of that diffraction condition, is an exact representation of the energy spectrum that we're putting in. It's just so cool. So that's what we're going to do. We're going to use our diffractometer to calibrate our X-ray source. Okay? So using a known crystal, we're going to use sodium chloride as a known because we know the crystal spacing of it to get this spectrum. And then we're going to take this spectrum and we're going to use that to figure out the spacings, the crystal lattice spacings of a bunch of other materials. Okay? So that's the X-ray lab. Any questions?
I don't understand the relationship between the spectrum and the diffraction effect, because the diffraction effect gives us the uncontinuous pattern, but the spectrum is continuous.
I'm sorry,
The diffraction effect gives us the uncontinuous pattern.
Yeah. But, and that's very true. If you're just looking at a white screen on a wall, then that's completely true, right? You'd see all of that stuff at once, right? But because we're repositioning the detector with every wavelength that we scan, so what you're saying is absolutely correct. If instead of having this detector here, we just looked at the wall and treated the wall with some X-ray sensitive paint, right? Then we'd see a traditional diffraction pattern. That, so we'd see something that looks like this, right? So we'd see that on the wall, right? But we're moving the detector as we change that angle. Okay, so we're just looking at one spot, right? And because we're looking at just one spot, we don't see this. Okay, we end up seeing this. Make sense? You don't look convinced. We can talk about it in a bit, okay? Any other questions? Okay, great. I won't keep you any longer. Thanks for coming. If you have questions, I'll stick around for a while.